so we learned about superpositions. Superpositions cause oscillations of observables or time dependence of observables through interference of the energy eigenstates. If we always, usually the basis we are considering is the energy eigenstate basis, but not always. We found out that if you have a superposition, the probability of being in any of the individual states does not change. It's fixed at the initial time. Now, of course, we need to get to a point later in this term where we allow those things to change. Everyone knows if you excite a fluorescent molecule, the ones in this ink, they go to an excited state, and then they emit light, and that light comes out. How does that happen? If you get changes by superposition, well, how on earth does the thing relax to the ground state again? Well, that obviously does not occur by unitary evolution, at least not unless you write a Hamiltonian for every single degree of freedom possibly related to those molecules. Instead, what we do is we couple the molecule to an environment, and to do that, we have to admit a loss of perfect information content. That is a very important concept. In traditional physics, even before quantum mechanics, we know how to deal with imperfect information. And I will hope that people have seen before the idea that if I make a constraint, a relatively weak constraint, which is that I propose that I know that I have an average energy for my system, it's fixed. If that's the case, then you can show by numerous different ways. One way, sort of using Lagrange multipliers, you can derive the Boltzmann relationship, which is to say, if I have the probability of being in a particular state, let's call it E sub n, it's going to be the Boltzmann factor, e to the minus en over kt, divided by the sum of all of the states. Right? So I will keep it discrete for now. So it'll be e to the minus en over kt. And then if you want to be extra careful, you can put in here also the degeneracy, which I'll just call W. Right, so you have that maybe some degenerate state. Then, of course, that increases the probability, but it also increases the so-called partition function, which is this. Okay, so we know how to deal with a system at some temperature. And that's the point. Temperature is the thing, the parameter, that encodes for us this lack of information content. Remember, one of the postulates of quantum mechanics is if you have a wave function or a state vector, then you have the entire information that you could possibly have. Well, if you have the entire information, then there's no ignorance. We have no ignorance. We might not like the fact that quantum mechanics tells us that electrons are diffusely, distributed around atoms and molecules, but nevertheless, that's the way it is. And we know what that distribution is arbitrarily well, provided we can calculate it. There's no ignorance. That means the entropy is zero. Well, the entropy can only be zero at one temperature. That means the temperature is zero. That's the third law of thermodynamics. There's no way around that. Quantum mechanics is not going to change it. What that means is that whenever you use the word wave function, meaning a specified state vector like this, you're automatically working in a situation where the temperature is zero, right? Where you have no ignorance. There's no lack of knowledge. The energy is the energy. Okay, well, that doesn't sound like real life, does it? We're going to put our molecules in solution. We're going to study, a psi3 molecule attached to some protein in a cell. That's not temperature equals zero, all right? Kt for normal, typical room temperature is about 200 wave numbers. But even at liquid nitrogen, it's still like 70 wave numbers or something. It's not zero. So there's always some energy. And that amount of energy that you have, this Kt amount, relative to your energy spacings, is going to tell you something about how likely you are to find the system just, randomly in an excited state, because that maximizes the entropy. There's more configurations when you can allow molecules to get excited even if it would seem like that would be bad because the overall energy goes up. Okay. So let's put this into more clear terms. Let's imagine I have these two states, N and M, or E and G if we want. I'm just going to call them G and E. Make the writing a little quicker. Okay. And what the Boltzmann relationship tells me that I can calculate the relative probability of having these two. So let's say the probability of being an excited state divided by the ground state. This is very important, right? This is something that a spectroscopist is always going to want to know about, especially people for whom this is a real problem, like in NMR. In NMR, the energy spacings are so close. KT is much bigger than the energy spacing, so almost the same number of spins are up as down. There's just a tiny little bit of a deficit for the higher energy state, and that's why you can even see an NMR spectrum at all. Okay, so the partition functions, this would be called Z. I'm going to ignore we'll set the degeneracy equal to 1, right? And so when we do this, it's going to be the Boltzmann factor, e to the minus EE divided by KT, divided by Z, divided by e to the minus EG over KT divided by Z. Okay, the Z's cancel, and so what we have is e to the minus the energy of the excited state. Oops, that's the wrong one. Energy of the excited state minus the energy of the ground state divided by KT. Right? So that's going to be, we can call it e to the minus delta E over KT, where delta E is equal to the excited state. Oh, I keep doing that. Excited energy divided minus the ground state energy. Okay, so that doesn't seem so bad. I could easily construct, a wave function that does this, right? We already looked at that. You just need to make a superposition. So let's say I have only these two states, right? And can I make a wave function that satisfies this? The answer is I can. Let's do it this way. So we're going to do psi of t, we're going to call it psi of t naught. And we're going to call that C of G times G plus C of E times E, right? Just some generic superposition, right? But one of those is going to be able to be consistent with this. We have one constraint, right? If we only have two states, we have one constraint on what these numbers are. To keep this normalized, we have to ensure that the wave function, that these probabilities have this property, which is really easy to show. If you just square this and then set it equal to 1, you'll find out that this has to be satisfied. It looks very much like sine squared plus cosine squared theta equals 1, right? Okay. So, no problem. We know these are the probabilities. This is the population of G. This is the population of E. So all we have to do is make sure that the ratio of those is this. Right? As long as the ratios of these two numbers is this one, then we know for sure the probability of being in the ground state will be the correct one that gives us this Boltzmann distribution, and the probability of the excited state will be the correct one that gives us that. Sounds good, right? Sounds like I can make a wave function that has the property of a Boltzmann distribution. Now, here's the problem, right? That's weird, right? Because this whole argument came based on an argument about ignorance. We said, we don't know everything. We do know that the average energy, we can certainly calculate the average energy here, which would be psi T naught times the Hamiltonian psi T naught. That would be the expectation value of the Hamiltonian. Right? You can work it out, but I'll tell you what it is. It's Cg squared times the energy of the ground state plus Ce squared times the energy of the excited state. It's just like the weighted average. Because of the orthogonality of these states, the cross terms go to 0, and all you're left with is the not cross term, so you get the square, and then you get the energy because the Hamiltonian operates on those. Okay, so this is the average energy. These values do not change as a function of time, so that means that the average energy will not change as a function of time either. Sounds pretty good. We have an average energy that doesn't change. We have probabilities of the states that don't change. So it seems like we're pretty good here. What's the problem? Okay, so let's think about what's the main condition for this whole thing that we started with. The main thing that we started with is that this is the Boltzmann relationship. The Boltzmann relationship assumes that the system's at equilibrium. All right, fine. So what would be a criteria for a system at equilibrium? The criteria for a system at equilibrium would be that nothing about that system changes, right? Certainly you don't expect to see a macroscopic change of something like a position or a momentum or angular momentum or the spin. You know they're fluctuating, but if you have enough things and they fluctuate, they average out to zero, right? Or the fluctuations average out to some average. It doesn't have to be zero. Okay, so the system should be at equilibrium. Well, what do we know about this system? Is it at equilibrium? No, because if I calculate anything else, any other observable, whatever that is, it's not going to be stationary. The expectation value, which would be the analog to the average in classical mechanics, right? We know what this is going to do. We just derived it last time. Right? It's going to be this complicated function. It has the coefficients in there, the relative phases. It has a time dependence. We know that this is a function of time. Unless it's energy, which is an observable, but not position, right? If this was the two states of a harmonic oscillator, then we calculate the expectation value of position. If these two states are like the ground state and the first excited state, the oscillator will be oscillating back and forth. That's not what you think of as an equilibrium system, right? So the problem with using a wave function is that you cannot produce a system that behaves according to the way we expect an equilibrium system to behave. Certain things about it are absolutely fine. The average energy is, in fact, stationary. The probabilities of the states or the populations of the states don't change. You can rig them up so that they satisfy a Boltzmann relationship. It gets more sort of involved, and the time evolution will be even more complicated if you have more than two states, because then when you evolve in time, you're going to have the interferences of all the pairs of states. Not just the two. All right, so from a practical point of view, a wave function cannot be used to represent a thermal distribution because it doesn't produce a proper equilibrium description of the behavior, right? And also, more philosophically, how can it possibly be consistent with a system that we just said is based on ignorance? It's derived from not knowing everything. Only knowing one constraint, the average energy. That gives us automatically, and you derive it. When you derive this, you find out that the temperature is something that emerges from the so-called Lagrange multiplier formulation. And then the temperature is essentially a gauge of how much ignorance you have. And that's why we have this tight integration between entropy and the minimum of temperature. When temperature is dialed all the way down, the entropy decreases to zero, the ignorance goes to zero. All right, so this is the conundrum. We cannot use a wave function when we want to have system at finite temperature. When we want to be able to reproduce a true equilibrium Boltzmann distribution, we cannot use a wave function because it has all these, the proper jargon to use is it has all these coherences in there. And those coherences do not show up at all in the population, but they absolutely will show up in anything else that's not diagonal with the Hamiltonian. It's not another operator that shares the same eigenbasis as the Hamiltonian, right? Something like position or momentum, whatever. Okay, so what do? It's actually kind of amazing. There is an analogy to the classical density operator, or classical density, phase-space density. So in classical mechanics, you have this phase-space density, this function that tells you about the density of points in position and momentum. Now we're going to be using my preferred notation for all this stuff, Q and P. So I think this comes from Messiah, but a textbook, and also from when I learned quantum mechanics in the Paul Brummer's class. But I think there's also a really nice sort of symbology to this. The Q and the P look much more similar to each other than X and P. Number one. Number two, we don't know how many dimensions are going to be. So Q can just stand for any kind of position you want. Obviously, I could have written it with a vector hat, thing. Right? But also, I like the idea that these are kind of like, sort of like Dr. Jekyll and Mr. Hyde, or like they're sort of like evil twins or something like that. They're related to each other by some duality. Now, what they're related to? They're related to each other basically by Fourier transforms, and that's very important. That's the basis of the uncertainty principle. Okay, so this is a perfectly reasonable thing to have classically. In a statistical mechanics class, you would spend a lot of time thinking about this classical phase-space density. Well, it turns out in quantum mechanics, we have something very similar, which is the quantum mechanical density operator. So a word about nomenclature. You will hear me and everybody else say density matrix a lot, okay? It's the same thing, except when you make a matrix of an operator, you've chosen a basis in which to express that or represent that operator. And there's just no way to get people to stop saying density matrix. It's just the way you say it. We're going to be drawing a lot of density matrices as well, so it's totally reasonable to use that terminology. But of course, you should think of it as an operator in Hilbert space, and that is what we're going to do. Okay, so it turns out the density operator has an interesting history. The person who really formulated the rigorousness of this is someone named Emmy Noether. And besides the Madame, Marie Curie, she's actually one of the only other key women in the development of modern physics who even anybody knows about. Emmy Noether now at least has been recognized somewhat retroactively, I guess, by some prestigious fellowships in the European Union for postdocs, I think. And so her work was at a level of theoretical physics and math beyond my comprehension. When I first learned, I was like, oh, that's really so cool. There's an important, super important, especially for chemists, development in this structure of quantum mechanics that came from a woman. I tried to read the paper and I just could not get past page 1. It's very complicated. But basically it tells us about the existence of a density operator, and that it follows from some extraordinarily complicated sort of symmetry arguments. So I'm not going to try to explain that. I will say that we owe to her, though, the solid foundation of the density operator.